We will now finish up partial derivatives by looking at a directional derivative. So remember that when we were studying partial derivatives originally, when we first started looking at them, we saw that a partial derivative is the slope of the tangent line that is parallel to that specific axis, i.e. the partial derivative with respect to x was the slope of the tangent line that was parallel to the x-axis. However, tangent lines do not need to be parallel to a coordinate axis. So the question then arises, how can we determine the slope of these? So what we wind up computing is the derivative that happens to be in the direction of the line, of the tangent line that we're looking for. Right? So we start with the graph of a surface that is defined by the equation z equals f of xy. Now, if we're given a point AB in the domain of f, we must choose a direction to travel from that point. And we measure this direction using an angle theta, which is measured counterclockwise, which will thus be shorthanded as CCW in the xy plane from the positive x-axis. So the angle is measured as we would normally measure an angle. The distance we travel is h, and the direction would then be given by the unit vector u equals cosine of theta sine of theta. So the z coordinate of the second point on the graph would be given by f of a plus h cosine of theta, b plus h sine of theta. And the slope of the secant line that connects these 2 points can be found by the difference in the z values divided by the length of the line. So slope is m equals f of a plus h cosine theta, b plus, I forgot to put an h in here, so this should be b plus h sine of theta, minus f of ab all over h. So the slope of the tangent line in the same direction would then be the limit of this slope here as it approaches 0. And that would be our definition for the directional derivative. So suppose that z equals f of xy is a function of 2 variables with a domain D. We let AB be in the domain, and we define u equals cosine of theta sine of theta. So that is our direction vector. Then the directional derivative of f in the direction of u is given by that limit that we've talked about earlier. And again, this should be an h here. And it's represented as this, so d of f of ab in the direction of u, provided that this limit actually exists. As with every other kind of derivative that we have studied, this definition is not practical to actually compute the derivative. So let z equal f of xy be a function of 2 variables, and assume that f sub x and f sub y both exist. So we are looking at the derivative that is in the direction of this vector. So let x equal a plus t cosine of theta, and let y equal b plus t sine of theta. Then define g of t equals f of xy. Since x and fy both exist, the chain rule would give us g prime of t is partial x times dx dt plus partial f partial y times dy dt. So this is f sub x of xy times dx dt is right here. I'm sorry, no, it's not. It's this here. Dx dt here would be cosine of theta plus f sub y of xy, and then times dy dt, so it's the derivative of this up this here, which is just sine of theta. Now, if t is equal to 0, x is equal to x of 0, and we denote that as x naught, and y, it would be equal to y of 0, and we denote that as y naught. So g prime of 0 would equal f sub x of x naught y naught times cosine of theta plus f sub y of x naught y naught times sine of theta. Now, on the other hand, we also have the limit as h approaches 0, g of h minus g of 0 over h. This is g prime of 0. Well, remember what g of x was. So g of h would be f of x naught plus h cosine of 0, comma y naught plus h sine of 0, minus f of x naught y naught all over h. But this is the directional derivative of f of x naught y naught in the direction of u. And so we've now determined a way that we can actually compute a directional derivative. We let z equal f of xy be a function of two variables and assume that fx and fy both exist. Then the directional derivative of f in the direction of u is given by f sub x of xy times cosine of theta plus f sub y of xy times sine of theta. So we wish to find the directional derivative of this function here in the direction that has the angle theta is the inverse cosine of 3/5. Then we wish to evaluate the directional derivative at the point negative 1, 2. So first what we need to do is we need to determine, well, what actual direction is this? So we're going to go back to right triangle trigonometry. So let's say this will be our angle theta here. So this is the inverse cosine of 3 over 5. So cosine of theta, remember, is adjacent over hypotenuse. So this would have to be 3, this would have to be 5. Well, this is clearly going to be a 3, 4, 5 right triangle, so that length is 4. So u is cosine of theta in the I direction plus sine of theta in the J direction. So this winds up being 3/5 I hat plus 4/5 J hat, right? Because remember, sine was opposite over hypotenuse. Okay, good. So we now have our unit vector. Now we take f sub x, which will be 2x minus y, and f sub y would be negative x plus 6y. So our directional derivative would be f sub x times the 3/5 plus f sub y times the 4/5. So we'll wind up with 6x over 5 minus 3y over 5 minus 4x over 5 plus 24y over 5. And if we completely simplify this, we have 2x over 5 plus 21y over 5. So now all we have to do is plug in negative 1, 2. So our derivative of f in the direction of u at the point negative 1, 2, negative 2 over 5 plus 42 over 5. This winds up being 45ths, which is just simply 8. So now we introduce a new operator. So the first thing we do is we notice, well, we can write the directional derivative as a dot product, right? If we look back, it's going to be the dot product. Here's a vector, fx, fy, and then the vector cosine theta, sine theta, which is right here. Well, we already know what this vector here is. This is u. So the question is there a way to represent this vector? And we can by introducing a new operator. This is known as the del operator. So the del operator is this upside down delta, which is the nabla symbol, and it is defined as del is the vector partial partial x comma partial partial y. And keep in mind that this does not need to be just two-dimensional. The del operator can be as many dimensions as needed by simply adding the appropriate partials, right? So if it was three-dimensional, del would be partial partial x, partial partial y, partial partial z. Right? And again, if we want to go into 4 dimensions, 5 dimensions, whatever, we just add the appropriate number of partial derivatives. Now, it's also important to note that this is an operator, which means on its own, it makes no sense. It has to be attached to something. So if you just write this, that makes no sense. You'd have to write, for instance, del of f, right? And then it would make sense. It's now attached to f. So this operator is now operating on f. So again, this is not really a vector per se, because it's an operator. Now, this happens to be, personally, one of my favorite operators in all of mathematics. It has so many uses in the field of physics. One of the uses we can make out of this, I just wrote. It's this right here. This is known as the gradient of f. And it is defined, del of f is simply the vector partial partial x of f, comma partial partial y of f. Now with the del operator, we have an alternative formula for the directional derivative. It is simply the gradient of f dotted with the direction of the vector. Now, again, it's very important to note this must be a unit vector. Right? One of the most common mistakes when calculating a directional derivative is students don't convert this u into a unit vector. Right? They just use any old vector. Now, an interpretation of the gradient. What exactly is the gradient? Now, let's take a look at this. If the angle between the gradient of f at x naught, y naught, and u is given by phi, then the directional derivative at f of x naught, y naught would be the magnitude of the gradient of f times the cosine of phi. Right, again, because the directional derivative is the dot product between the gradient and u. If phi happens to be 0, then this becomes simply the magnitude of the gradient. And that gradient and u would point in the same direction. If phi happens to be pi, then this directional derivative becomes negative the magnitude of the gradient, and the gradient and u happen to point in opposite directions. For values between 0 and pi, we would have the directional derivative is between negative magnitude of the gradient and positive magnitude of the gradient. And if the gradient happens to be the 0 vector, then the directional derivative is 0 no matter what direction we're looking at. And we summarize this now in the next theorem. So the two important ones out of here is we can maximize the directional derivative, or the directional derivative is maximized in the direction of the gradient. So the direction of maximum rate of change is in the direction of this gradient. And the value of that maximum rate of change is the magnitude of the gradient. The direction of minimum rate of change is negative gradient. And it has a minimum value of the negative magnitude. All right, we're going to look at this now. So we want to find the direction for which the directional derivative of this function at the point negative 2, 3 is a maximum. And then what is the value of that maximum? So first, calculate del f, because this will give us the direction of maximum increase. All right, so we'll have 6x minus 4y, and then negative 4x, plus 4y. And again, because remember, the gradient of f is partial f, partial x, partial f, partial y. So this would mean then that the gradient of f in the direction of negative 2, 3 is 6 times negative 2, so negative 12 minus 12, that's negative 24. And then negative 4 times 3 is negative 4 times the negative 2 is 8, plus 12 is 16. And I'm going to go ahead. All right, so I made a mistake. This is not actually 16. This should be 20. All right, so we can factor out a 4 from that. And we'll be left with negative 8 comma 5. I'm sorry, I'm really off my game. That should not be negative 8, that should be negative 6. So what this is saying is that the direction of maximum rate of change is negative 2420. Right, so if we look at our graph, so we're at the point negative 2, 3, that would be somewhere here. Negative 2420, that's going to do something like this. All right, so that would be the direction of maximum increase. Now, what is this actual maximum increase? Well, that is just the magnitude of the gradient. So we're going to have 4 times the square root of 36 plus 25 which is 4 times the square root of 61. So that is the value of the maximum increase. Max, I should say rate of change, not increase. Right, so that is the gradient, and that's also the directional derivative. So we have now concluded partial derivatives. In the next video, we're going to start with multiple integration. And this is where this course will really begin to take off in difficulty. So if you've been bored up to this point, that is about to change.